Hello everyone. This is part 2 of our lecture series regarding series solutions of ordinary differential equations. In part 1, we have mentioned that there are at least two techniques of solving ordinary differential equations. We have by substitution of an exponential ansatz and through the Frobenius method. We have introduced the substitution of exponential ansatz wherein we just have to substitute the ansatz to our general form of or general equation of the ordinary differential equation, and then find the roots of the quadratic equation and refer it to the four cases that I've mentioned earlier in part 1 for the general solution. Now we will try to apply that concept to this linear oscillator model given by d squared of y with respect to t plus omega squared y is equal to 0. So these are the steps that we follow for us to be able to find the general form of the solution. The first one is of course to consider an exponential ansatz, and we can notice here that our linear oscillator model is as a function of t. So our exponential ansatz in this case must also be as a function of t, and that is given by y is equal to e to the pt. And then we substitute this ansatz to our equation, particularly to the second term for y, and then look for the second derivative and substitute it back to our linear oscillator equation. After that, we then find the general form of the solution and apply identities if applicable, as the case may be. So we proceed with the first step. The derivatives of y is equal to e to the pt. So we first find the first and second derivatives of our proposed solution. Here we have dy over dt, or simply just y prime, is equal to p e to the pt, and of course our second derivative is given by p squared e to the pt. And then we substitute the exponential ansatz and the second derivative to our general equation, which is d squared of y with respect to t plus omega squared y is equal to 0, and upon substitution we get this equation. Now obviously we have a common term, we have e to the pt, so we eliminate that by dividing both sides by e to the pt, so that what's left is p squared plus omega squared is equal to 0. By transposing omega squared to the other side and by getting the square root, we found that the roots, or that the solution is actually plus or minus I omega. Upon getting this, the next question to be answered is, among the four cases that we have shown in the previous video, which of those is applicable in this case, so that we can have the general solution for our linear oscillator model. Now, we recall that the fourth case that I've presented in the first part of the video gives us this general oscillatory or underdamped solution in case where there are two complex conjugate roots. Now, in our case, we have our root is plus or minus I omega. Obviously, we have r is equal to 0 in our case for the linear oscillator model. So by applying this, we get this solution. We have y as a function of t equals e to the rt times the quantity c1 cosine of omega t plus c2 sine of omega t. Obviously, we don't have a value for r. This is equal to 0. So we eliminate this. And this gives us y as a function of t is equal to c1 cosine omega t plus c2 sine omega t. Now, this is the final answer, but if we want to apply some applicable identities, we can actually apply the Euler's identity. So that is given by these two equations, e to the I theta equals cosine of theta plus I sine of theta, and e to the negative I theta equals cosine of theta minus I sine of theta. And by applying this Euler's identity, we can directly see that y as a function of t equals c1 e to the I omega t plus c2 e to the negative I omega t. And this is our final answer. This is the exponential form of our final answer by making use of the ansatz that we have introduced earlier, that is y is equal to e to the pt. Now obviously this is just one of the many techniques that we can use in solving the linear oscillator model. We have also other techniques, and in our next video we will be introducing the Frobenius method, and we can notice that the solution that we can arrive using the Frobenius method is also the same as this solution. That's it, and thank you for watching.